Hi students, in this lecture I am going to discuss thermodynamics. Let us see list of concepts. First law, second law, and in that Carnot engine and entropy. Let us see first law. Consider an ideal gas in a vessel with a piston. So take a vessel. So taking a vessel with a piston. It is now enclosing an ideal gas. Now provide some energy, heat energy to system. So when we provide heat energy, gas will expand. That means piston moves upwards. So some of the heat energy given to system is utilized for doing work done, and remaining is now increasing the internal energy of the system. That means we can write Q equal to delta U plus W. See, this is nothing but energy conservation. So amount of heat given, some part of that utilized for doing work done, remaining is now increasing system's internal energy. So this is nothing but law of conservation of energy. And this is known as first law of thermodynamics. And writing same thing in differential form, that is dq equal to du plus dw. This is known as differential form of first law. Let us see how to calculate q. So q equal to, it is n c delta t. That means when we are providing heat energy to system, delta T refers to change in temperature of the system. This change may be positive, may be negative. If heat is given to system, then delta T is positive. If heat is taken from system, delta T will be negative. That means when you are taking the sign convention, Q is positive if it is given to system, Q is negative if it is taken from system. And coming to C, it is a molar specific heat which depends on the process. For example, if it is constant pressure, C will be Cp. If you are taking constant volume, then C will be Cv. Like this. This C depends on the process. And N is number of moles. And coming to delta U, change in internal energy, which is equal to N Cv delta T. So again coming to here, Cv, molar specific heat at a constant volume. It is molar specific heat at a constant volume. But remember, this is not only for constant volume, for any process, delta U is given by NCV delta T. This is for any process for an ideal gas. Now coming to W. W is given by integration of, see how to calculate this. According to definition of work done, line integral f bar dot ds bar. Now see in the place of force what we can write. Suppose gas is now expanding. Gas expanding means force by the gas on the piston is outwards and piston moves outwards. So force and displacement both are in the same direction. So I can write here F is pressure of the gas into area of the piston, that is a force, ds. Suppose a piston moves by a small distance. So take it as a dx, a small distance. Then it is into dx. And between these two angles is now 0. So it is a cos 0. Now see carefully. Area into dx. This is giving us small change in volume. Area of the piston. This is moving by small distance dx. So A into dx gives us change in volume. Means you can say small change in volume. That means now this becomes P dV, right? That means whenever we want to calculate work done, it is integral P dV, where P stands for pressure of the gas. So in this we have to focus. W stands for work done by the system. The meaning of W is work done by the system, and that is given by integral P dV, where P is pressure of the gas. And this will be positive if gas is expanding. You can see here we have taken cos 0 because pressure is now means force by the gas is outwards. Displacement also outwards means expansion. So cos 0. So work done by the system is a positive. If gas is compressed by the gas, force is outwards, but displacement is downwards. That means it will be cos 180. That means work done by the system is a positive if gas is expanding, negative if gas is compressed. Okay. And coming to here, dq. dq means, so this is known as differential form. So dq means it is Nc dt, small change in temperature. Du. Du is Ncv dt. And dw, that is pdv. Means when we integrate this one, we are going to get a q value. After taking integration, we are going to get q value. In the same way, integration of du, that gives us delta u, right? In the same way, integration of dw, that is giving us work done by the system, right? Let us now focus some standard processes. Application of first law. Let us consider isothermal process. Isothermal process. So isothermal means temperature is a constant. It is a constant. So temperature constant means from gas equation we can write PV equal to nRT. So for a given system, that means number of moles constant and R is a constant. When T constant, PV is a constant. So from this we can write PV is a constant. So whenever it is given isothermal process, PV is a constant. And next we can say here delta U value, which is now internal energy, it's a change. And we are knowing that it is a function of temperature. So since T constant, delta U is 0. Since delta U 0 from first law, Q equal to W. So here one condition is that for the process to be isothermal, The walls of the vessel must be conductive and the process must be done very slowly. I am repeating, the walls, or you can say base. The vessel must be conducting one. Next, the process must be done very slowly. Relation is that when it is expanding very slowly, then while expanding, while expanding, you can see energy is given to system, and when it is given to system, this is a completely converting into work done, completely converting into work done. Suppose we are taking the reverse speed, we are doing work on the system. When we are doing work on the system, that means W will be negative. When W is negative, Q will be negative. That means heat is given by the system to surroundings. When process is taken very slowly, it is having sufficient time to exchange energy with the surroundings. That's why process must be done very slowly. So condition 1, the conductor means the vessel must be conducting one and process must be taken very slowly. Now see delta U0 Q equal to W and see how to calculate now W value. Coming to calculation of W, W equal to integral P dV. In the place of P, we can write from gas equation nRT by V into dV. So number of moles constant, R is a constant, T also constant, take outside. So nRT taking outside. Remaining is now integral dV by V. That is ln V. It is ln V. Now take limits, initial volume. Take it as V initial and this is V final. So that is equal to nRT ln V final by V initial. And this is to the base E. Or if you want to convert into base 10, this is 2.303 nRT log to the base 10 V final by V initial. So this is now expression for work done in isothermal process. And next see what else we can say regarding this process. And regarding this, if you are taking molar specific heat, see how it is defined. C equal to dq by n dt. And in this process, dq is non-zero, but coming to dt, it is 0. That means C value is infinity. That means for isothermal process, molar specific heat is infinity. And see what else we can say regarding this. If you want to calculate bulk modulus for this process, see expression for bulk modulus. Expression for bulk modulus. See how bulk modulus is defined. Right, bulk modulus is given by B equal to delta P by minus delta V by V. See how to calculate that. So we have condition PV equal to constant. Now differentiate that. See it becomes P dV plus V dP is equal to 0. See from this what we get dP by delta V by V. I can write P equal to minus dP by dV by V. See carefully once. P dV plus V dP equal to 0. Differentiating PV equal to constant. Then P equal to minus dP dV by V. That means bulk modulus for isothermal process is equal to pressure of the gas. It is equal to pressure of the gas. Okay. So there are some important points regarding isothermal process. Let us focus now next adiabatic process. So adiabatic process means first condition, the walls of the vessel must be non-conducting, or you can say insulator. That means no heat is given to system and no heat is taken from system. So first condition is a Q equal to 0. Then see what we can write from first law. Right. Coming to adiabatic process, it is adiabatic process. So for that, Q equal to 0, condition 1. That means no heat energy given to system or no heat energy taken from system. So Q0. And from first law, Q0 means delta U should be equal to minus W. See meaning of this. When gas is expanding, W will be positive because W stands for work done by the system. So expansion means W is positive. When W positive, delta U will be negative. So its meaning is that work is done by utilizing some of its internal energy. Therefore, delta U will be negative. That implies when gas is expanding adiabatically, its temperature will decrease because delta U is negative. Okay. Now let us focus how to calculate work done in adiabatic process. So adiabatic process condition Q0 and we got here delta U equal to minus W. First focus any equation available just like PV equal to constant by using these two conditions. See what we can write here. Delta U that is N CV dt that is equal to means if you are taken now in differential form, let us take differential form here. So taking differential form, du is equal to minus dw. So it is now ncv delta dt is equal to minus pdv. This is take it as equation 1. Let us take now from gas equation PV equal to nRT. Now differentiate that gas equation and see what we get. So PdV plus VdP is equal to nRdt. So this is by differentiating gas equation. Okay. Take this as equation 2. Now see what we can write here. In the place of in the place of dt, what we can write? Dt equal to pdv plus vdp by nr. So I'm taking from equation 2 the value of dt and substituting that in equation 1. See carefully, in equation 1, it is n cv in the place of dt. So it is now pdv plus vdp upon nr, pdp upon nr, that is equal to minus pdv. Okay, let us erase this one. Then see remaining calculation part. Right now we can simplify this. N gets cancelled. Remaining is now take minus pdv left side. See what we get here. Cp into pdv plus, sorry, cv, right? It is cv. It is cv. So it is now cv into pdv plus cv into vdp plus it is r into pdv, that is equal to 0. So in this I can take pdv common here, pdv. So pdv into cv plus r. Okay, these two, pdv plus it is into cv plus r plus cv into vdp equal to 0. Now we are knowing that cv plus r is equal to cp, that is now cp into pdv, that is equal to minus cv into vdp. Now rearrange this. Now rearranging this one. So when we rearrange this, see what we get. Cp by cv. Cp by cv into, it is Cp by cv into dv by v. dv by v is equal to minus dp by p. Check it once. I have taken Cp by cv. dv by v is equal to minus dp by p. Cp by cv is known as gamma, right? Now integrate this. Now integrate. Then see what we get. Gamma ln v plus ln p equal to 0, right? So now this can be taken as it is v power gamma, and this is log a plus log b. That becomes p V power gamma equal to constant. That means for adiabatic process. For adiabatic process, equation is P V power gamma equal to constant. That is what we got from Q equal to 0. From that condition, du equal to minus dw. And next we are taking that from gas equation and simplifying those. We have condition P V power gamma equal to constant. Now we can see from gas equation, PV equal to nRT. This is in terms of pressure and volume. Let us take this in terms of temperature and volume. Then see what we can do. In the place of pressure, we can write nRT by V in the place of pressure into V power gamma equal to constant, right? nR constant, this is V power gamma and this is V. So remaining is now T, V power gamma minus 1 is a constant, right? One more result. So in terms of P and V, in terms of T and V, so remaining is now in terms of pressure and temperature, okay? Pressure and temperature. Then see what we can do. In the place of volume from gas equation, so this is a pressure. In the place of volume, writing nRT in the place of volume nRT by P all power gamma that is equal to constant. Then see what we get. nR, it is a constant. This is a P power gamma. So P power 1 minus gamma, P power 1 minus gamma, T power gamma equal to constant. Okay. So you can take this is 3. This is a 4 and this is a 5. So these three equations we have to keep in mind for solving problems based on adiabatic process. So P V power gamma equal to constant, T V power gamma minus 1 constant, P power 1 minus gamma, T power gamma is a constant. Okay, right. Now focus on what is adiabatic. See in adiabatic process, what is molar specific heat? Definition part C equal to dq by n dt. Now in this, no heat is given, no heat is taken, right? That means molar specific heat for adiabatic process is 0. Okay. Next, if you want to calculate bulk modulus for adiabatic process, then see what we can do. Take P V power gamma constant, differentiate that. See what we get from that. P gamma V power gamma minus 1 dV plus V power gamma dP equal to 0. Okay. Differentiating P V power gamma equal to constant. See once P gamma V power gamma minus 1 into dV plus V power gamma into dP equal to 0. So here what we can do is we can cancel V power gamma minus 1. So here 1 V is left, right? This is P dV gamma that is equal to minus V into dP, right? See from this what we get dP by, so gamma P is equal to minus dP by dV by V. Check it once. dP into V by dV. Now that is taken as dV by V, right? Now this is nothing but a bulk modulus. That means for adiabatic process, Bulk modulus is gamma times pressure of the gas. Whereas for isothermal process, bulk modulus is equal to pressure of the gas. Okay. Let us now calculate work done in this process. Calculation of work done for this process. Work done is equal to integral P dV in the place of pressure. What we can write? Right. We want to calculate now work done in this process. W equal to integral P dV from this equation P V power gamma equal to constant. Let us take it as some constant K. Then I can write in the place of P that constant K upon V power gamma dV. Now take limits V. V initial to V final. I'm taking K outside. This is V power minus gamma into dV. That becomes V power minus gamma plus 1 upon minus gamma plus 1. Now substitute values. Initial volume, take it as V1, final volume V2. It is now, I can take 1 minus gamma outside. It is 1 by 1 minus gamma. Remaining is now, let us take K value inside. Take K value inside. K into V2 power 1 minus gamma minus K into V1 power 1 minus gamma. Okay. Now take in the place of K P V power gamma. So P V power gamma means V power gamma, V power minus gamma gets cancelled. Okay. So remaining is now 1 by 1 minus gamma. It is P2 V2 minus P1 V1. See carefully once, okay? In the place of K, P V power gamma. Now substitute here P2 V2 power gamma. V2 power minus gamma gets cancelled. Remaining is V2 power 1. So P2 V2 minus P1 V1. Okay. This can also be written as P2 V2 minus P1 V1. From gas equation, it is equal to NR delta T, means T2 minus T1. So you have to keep these 2 points in mind. Work done in adiabatic process is 1 by 1 minus gamma into P2 V2 minus P1 V1. Okay. Or it is NR delta T. Delta T means T2 minus T1. Okay. By 1 minus gamma. See, we have seen that during expansion, temperature of the gas decreases. That means dT will be negative. And we can see here gamma is greater than 1. So 1 minus gamma is negative. This is negative. dT value negative. Negative becomes total value positive. That means during expansion W is positive. Okay. And remaining process we can discuss in next lecture.